Hello everyone, today we're talking about modeling with exponential and logarithmic functions. So we're going to solve word problems that involve exponential and logarithmic functions, section 4.5 in our book. Here you're going to want to make sure you get down the exponential growth model, n of t obviously being our total, n sub 0 being our initial, the mathematical constant e, and then that is raised to the rate of growth and the amount of time. So go ahead and get that down in your notes. And the decay model you're going to want. The total equal to the original mathematical constant e raised to the negative r. R is equal to the ln of 2 divided by h. And then you take the negative r and multiply that by time, and that whole thing is our numerator. And you'll see in the examples what I mean exactly by that. But make sure you have the growth and decay model in your notes. The book will tell you when you're supposed to use the growth model and when you're supposed to use the decay model, but hopefully by the end of the lecture and the end of the practice problems, we'll know when to use the different equations, different formulas. So the first, a culture starts with 10,000 bacteria, and the number doubles every 40 minutes. So first, they want us to find the function that models the number of bacteria at time t. So they've given us the starting amount. So again, I'll write down. So total is equal to the original e to the rt. Okay, so they give us, it starts with 10,000. They give us 40 minutes. They do not give us the rate. So we know it doubles every 40 minutes, right? So if I start with 10,000, we know after 40 minutes, I'm going to have 20,000 bacteria. So now I go ahead and solve for r. So 2 equals e to the r times 40. And now here, we can use what we did in 4.4 to go ahead and solve for r. So I'm going to take the ln of both sides. So if I take the ln of this side, we know that the ln and the e cancel. So I'm left with just r times 40. And when we divide by 40, we find our rate equals 0.01733, meaning that our function for a in terms of t looks like so our total, therefore, 3 dots means therefore our total is equal to 10,000, our initial bacteria, times e raised to the 0.01733 times t. So now we can find how many bacteria there will be at any given time t. And we'll get to that graph. B, find the number of bacteria after 1 hour. So you have to be careful here. They say after 1 hour, but we know that the bacteria are in minutes. They're growing in minutes. So you have to turn your hours into minutes. So part B, n of t equals 10,000 e times 0.01733, and then we're going to multiply it by 60 because there are 60 minutes in 1 hour, and when you use your calculator to compute that, you get there will be 28,286.51 bacteria, roughly. C then asks, how many more minutes will there be 50,000 bacteria? So now we're going to be solving in how many minutes? We're going to be solving for the variable t. So we know we want to figure out how long it'll take to get to 50,000. We know my rate. In this case, we do not know how long it'll take to get to 50,000. So first thing I'm going to do, move my 10,000 to the other side. So when I divide both sides by 10,000, I get 5 equals e raised to the 0.01733 times t. Right? And then we're just going to do the same process we've done before. Take the ln of both sides. Right? And I didn't have to rewrite ln of e because ln of e just cancels to 1. And then I go through and divide by my rate. So I find my time, it will take me 92.87 minutes. So that's C, that'll take me 92 minutes. Then just sketch a graph. So here I already have the graph for us. Our y-intercept is going to be 10,000, and it's going to grow exponentially from there with the number of bacteria growing exponentially. Right? Because we have our variable is in the exponent, so it's going to grow exponentially. So that was a growth one. Now let's use a decay one. So it's easy to see this one's decay because it says half-life. So half-life meaning we're losing a certain portion. We're losing, well, in fact, half-life, we're losing half of whatever we started with in a certain number of time, in a certain amount of time. So suppose this sample has 300 milligrams and its half-life is 140 days. So the first thing we're going to have to do is find the function. And in order to find that function, first we have to find our rate. But remember, our rate, let me write the decay down again. So m of t equals m0 e to the negative rt. And remember, our r is equal to the ln of 2 divided by whatever our half-life is. So in order to find the rate, you just plug the half-life in here. They'll typically give you the half-life. Maybe some problems they'll give you everything else, and you have to find the half-life. But at least for this example, they've given us the half-life. So let's find the rate so we can plug it in to get the equation. So r equals ln of 2 divided by a half-life of 140. And that gives us 0.00495. The calculator actually gave me 4.95 e to the negative 3. So remember, that's just scientific notation in our calculator. You just move it 1, 2, 3 spots to the left. Right? 1, 2, 3 spots. And this is our rate. So now that function looks like m of t is equal to the initial we started with, 300 milligrams, times e raised to the negative 0.00495, and then however long we're talking about, however many days in this case, because the half-life takes 140 days. That's A. B. Now they want us to find the mass remaining after 1 year. Again, be careful. A lot of people will put 1 in for 1 year, but remember a half-life is measured in days, so make sure you're putting in the time in days. So this comes later. B. They want to know after 1 year. So I'm going to use my equation, and my time is going to be 365 days in 1 year. So how many do I have, or how much is remaining? And 365, make sure you put this entire exponent in parentheses, and we see that there is 49.26 milligrams of plutonium-210 remaining after 365 days. Now that makes sense. It makes sense that there would only be 49 milligrams because the half-life is 140 days. So a half-life means after that certain amount of time, half of the mass is remaining. So after 140 days, there'd be only 150 milligrams left. after 280 days, 2 half-lives, you take half of that again, there's only 75 milligrams left. And since there are 2.6 half-lives in a year, right? If you did 365 divided by 1.40, or 365 divided by 140, you get about 2.6 half-lives. So it makes sense that there's less than 75 milligrams left. And see how long will it take to decay to 20 milligrams. So now they've given us 20 is our total. They want it to be at 20. We started with 300. We got negative 0.00495. And we do not know how long that'll take me to get to 200 milligrams yet. So divide by 300, I get 2/3. And then take the ln of both sides again, so I get the ln of 2/3 equals negative 0.00495t. And when you divide both sides by negative 0.00495t, you get, negative 0.00495, obviously don't divide by t, you get 81 days. So not quite one whole half-life, right? Because I still had 200 milligrams more than half of the original, so it can't even be an entire half-life. So that was C, and finally, draw a graph. So here I have a graph. We're crossing at 300. My y-intercept is 300, but now you can see, right, that I'm decaying. I'm losing the amount of plutonium left. And hopefully we're catching on that 300, the leading coefficient there in front of my mathematical E, was my y-intercept. Right, I can't have anything to the left. That's why I cut the graph off here, because you can't have a negative time. Time can only go positive. So we're always going to start, at least in this case, at 0 when we're talking about time. Next problem. Now I can see from this one that we've got growth rate. So I'm going to go right to my growth model. And so again, just one more time, I'll write the growth down. And the first one, let's see, we have 5.7 billion in 1995. Growth rate was 2% per year. By what year will the population have doubled? So if I want the population to be doubled, I've got 11.4 billion people. I started with 5.7 billion people. My mathematical E stays constant, and my growth rate is 0.02, standing for 2%. I don't know how long it's going to take me to get to 11.4 billion. So let's see, I divide by 5.7. That gives me 2. Again, take the ln of both sides, so ln of 2 equals 0.02t, and divide by 0.02 to see that it would take me 34.66. So in order to actually reach 11.4 billion, that's going to take me 35 years, and it wants to know in what year. So I started in 1995, it takes me 35 years, so by the year 2030, we'll have 11.4 billion according to that population growth. Then they want to know by what year will the population have tripled. So same process. Instead now, 5.7 tripled is 17.1 billion. So I'm going to divide by 5.7, and I get 3. That should be a, just want to make sure, 5.7. I get 3, and e to the 0.02t. Again, ln of both sides. And divide by my rate. So now it's going to take me 54.93 years. So in order to reach that triple amount, I'm going to have to actually take 55 years. So we're talking about the year 2050. We'll have 17.1 billion people according to that growth model. Last example. It says we are containing 59% of the carbon-14 it originally obtained, or contained originally. So we can see since it's less than the 100% it started with, this is going to be a decay model, and they even say the half-life is 5,730 years, so it's going to be a decay model. Again, decay model looking like and remember that R is equal to the ln of 2 divided by the half-life. So they want to know how long ago the mummy was buried. So the first thing I'm going to do is, let's see, I have 59% currently. I started with 100%, right? It's only 59% of the carbon-14, but obviously it started with 100% when they first put the cloth on the mummy. And that's multiplied by e to the negative, and then my rate is going to be ln of 2 divided by the half-life of 5,730, and then that is all multiplied by t, right? And they want to know how long ago, so we're going to figure out how much time has passed to get me to that amount of carbon-14. And they actually use this type of radioactive decay to age things like this in the pyramids and other artifacts that they find. They use this type of math. So go ahead, divide by 100, same process as before, and then we get e raised to the negative ln 2 over 5,730 times t. And again, take the ln of both sides. So I get the negative ln 2 over 5,730 times t, and then obviously divide by negative ln 2 divided by 5,730, so I'm going to divide by all of that. Let's just make sure we keep that part in parentheses. And our t is equal to 4,361.75 years ago. So that's how old that mummy is. That mummy is 4,361, pretty much 62 years old. So go ahead and use these growth and decay models to try the example problems that accompany this in the PowerPoint, and we'll talk about it in class again tomorrow.